So tonight we're kind of reverting back to the, well, I am to the drinking and talking mode. So I'm limiting it to one gin and tonic, so I won't slur too much. So tonight we're going to talk about the new version of the MCP. So we've got about 48 people on. The new version is, like all upgrades, more complicated. It will be a bit of a learning curve to learn the new features, but what I've added is the Baglioni style microemulsions. And these are, I'd say, the third new wave of technology for cleaning systems. Luke's been using them extensively. He's had a lot to do with the systems. Actually, all the recipes are from him. He's proofed them out. He's like our, the baking, the person who double checks the recipes before they're printed in the newspaper. So he's been doing that and finding little things. The other thing that he's found, which puts us, I think, a step ahead of Baglioni, is that, as you probably know, these are mostly water, between 60 and 90% water, with co-surfactants and surfactants and solvents added to make the microemulsion, the nanostructured fluid. We know with the MCP and all that you can get a lot of control just by adjusting the pH of the water, adding chelating agents to the water. Baglioni uses just distilled water. So what Luke's done is shown that if we buffer the water, if we add chelating agents to the water, we can control more precisely than the standard recipes that he's developed. That's not to take anything away from what he's done. And we have to remember his initial approach to all this was cleaning things like wax and B72 off murals. So that's a very different type of problem. Water's not, kind of water's water. There's a lot of ionic material. It's going to, shift probably pretty much any pH you put on there. That's where he started. That's where his mindset is. And also clearing, we can clear with, pH adjusted water, just like we know to do with a modular cleaning program. What I'm going to do is talk about the new system, kind of demonstrate it. It's not finished yet. It's very far along the way to being finished, and I hope to have it finished by Monday. What I'll suggest is that anyone who wants to try it out or use it can send an email, and also send you I'll send you the web address, or the Dropbox address for where the files are, and Luke's supply sheet, where he's found low-cost suppliers for pretty much everything we need. So how familiar is everybody with the Baglioni system, or the structured nanofluids, all that? Okay. I think I'll hand it over to Luke, and he can give a kind of a brief discussion and show some slides he's done. He's been working with these extensively, as have other people. The only time I've used them was on overpaint on a sculpture, and it's remarkable how these materials work. The whole concept of de-wetting, of mechanically pushing a swollen layer off the surface of an unaffected layer. It's a whole new mindset. It's a whole new approach. That's not to say that they can't be used like regular solvents, like a regular emulsion, where you actually just use it to bring things into solution. But there's this whole dynamic where you can use them to de-wet a surface and separate one layer from another very cleanly. The other thing before I hand it over to Luke is that Baglioni's come up with two things. He's come up with the microemulsions and he's come up with the gel systems. And we're not going to talk at all about the gel systems. They're also remarkable, the Peggy series, the Max Dry series, and some other ones that he's been working on apparently. But those, I think, are more evolutionary than revolutionary. They're great, but they're kind of better than agarose or something, but not, it's not a game changer like these microemulsions are. So Luke.
Yeah, well, maybe I'll contradict that really quickly and say that, as far as gels go, there are some really nice agaroses that are used more so in biochemistry and microbiology that work really nicely for this, that can give almost the same results as some of the Baglioni kind of medium dry gels. And those are the super strength agarose gels. And you can cast those into something like 2mm sheets and soak the gel in the microemulsion and get really good performance out of those. And a group and I have been testing that gel system, and it's been coming along really nicely. So that is an alternative. But there are a lot of other systems and ways that you can load the microemulsion into a poultice or something like that to bring to the surface of the artwork. Let's see, I'll share my screen really quick. Let's see. All right, can everybody see Baby Yoda? Thumbs up if you can see Baby Yoda. Perfect. That's my new shop assistant. Okay, so like Chris said, we're kind of going back to what the origin of this series was, which was a little more conversational and a little more laid back and a little less technical. So a lot of this that we're going to talk about concerning microemulsions is going to be a lot more practical. And if you have questions, throw them in the chat, because there's a lot that we can talk about. So if there are things that you're unclear on, just let me know and we can go over it, because there are a ton of places we could go with this. So to just kind of get started, a lot of folks think that microemulsions are really complex, difficult to make, just out of your reach. As a standard bench conservator, a lot of folks think that microemulsions are just, too complex. They're really not. If you're able to make a standard MCP aqueous solution, then you can make a microemulsion. There's really only one extra step, and that's adding a solvent. So if you can take the modular cleaning program, build an aqueous solution with a buffer, a chelator, and a surfactant, add one more step, which is adding a solvent, and you're there. So really the only special thing about a microemulsion are the proportions of those materials. And that's what we've worked out, and that's what Chris is going to show you later. We have those formulations ready to go, so you can prepare them just like you would any normal solution. So just to kind of reiterate that, this is my microemulsion kind of workstation that I have in my home studio. So you can see, very standard setup. I have a magnetic stirrer in the corner. I do have my fume extractor right here, which is really handy. One of those regular junky scales we were just talking about, that's $20 on Amazon, and you can see the surface here is destroyed by sodium hydroxide, so it's nice to have an inexpensive scale you're not worried about ruining. One thing that I really like for these, a really nice practical tip, is to have a 30 or 50 milliliter syringe with an 18 gauge needle. And a long needle is really nice because you can use that to withdraw the solvent from the container. I've noticed, especially working with students and other folks who don't handle a lot of solvents, that you tend to spill a lot when you're working with these big containers. So that really helps limit spills, especially when you're working in a home studio. You don't want to be spilling solvents on your surface, because then it evaporates in your workspace, unless you have a fume hood and you don't have to worry. But so that syringe is a really nice tip when you're making these, because you can withdraw an appropriate amount of solvent. If you need 8 milliliters, you can withdraw 8 milliliters, weigh it right on your scale, and then throw it into your container with your aqueous solution. So speaking of aqueous solutions, I have my aqueous solutions over here on the left side. And one of the things that Chris was just talking about, using buffers and chelators, You prepare your solution with your buffer and your chelator, and you check your pH. You add your surfactant, which will be given to you, the amount of that, and then you put your container with your aqueous solution right on your magnetic stirrer, and you can have your little solvent station right here, and you can add your solvents right to this pre-prepared aqueous mixture that you have. So it's a very easy, efficient way of preparing microemulsions. You can just set up a little workstation just like this, and it makes things, very simple. And I actually have on my 100 mil graduated cylinder over here some markings for standard microemulsions that I tend to make a lot. But really, that's it. So you can see I just have some standard MCP, materials ready to go. I have my solvents ready to go, and my syringe for withdrawing solvents, and that's about all you need to make these systems. It's nothing too complex. Always good to have some paper towels around because you will end up spilling things. So those are good to have. So, why would you add a buffer or a chelator? Chris kind of alluded to this already, but, one of the important things that we want to control whenever we're interacting with the surface are the acid-base reactions that are going to occur, because they will occur. When you add water to that system, there are, acidic decomposition products, all kinds of things on that surface that are going to react when you add water to it. So if you have a buffer in that system and you can control those acid-base reactions, that's always a plus. You have fewer unintended reactions occurring there. So a buffer is always a great idea when you're working with a surface. Another thing that's really nice with a strategically selected buffer is that if you select the right one, you can also help facilitate swelling of a coating. And swelling of a coating is really important when you're thinking about something like de-wetting, because the first stage of de-wetting is swelling. When you swell a coating, you're actually taking it from a solid to a fluid. So it's no longer a solid, it's a fluid. So as soon as you swell it, you're actually lowering the glass transition temperature at room temperature, and that enables you to de-wet the coating much more easily. Now, normally that's facilitated just by the solvent and the micelles within the microemulsion, so that swelling occurs, due to those. But if you add in that pH buffer, that boosts the swelling and also removes some other materials from the surface so that that coating can swell more thoroughly, more quickly, and improves reaction kinetics, all kinds of things. We can get into that if anyone wants to. The other thing is that adding a chelator is really, really beneficial when working with these systems kind of in the wild. If you work on private objects, a lot of times those objects come to your studio in an absolutely filthy state. Or you go on site and you work somewhere, those objects have a layer of grime and dirt and soil that, you maybe wouldn't encounter as often, if you're used to working with museum objects that are stored properly. So chelators are really nice because they can help remove a lot of cementitious soil or cementitious dirt that's essentially glued to the surface. So if you're able to remove that soil layer, then that microemulsion, the micelles, can penetrate into the coating much more easily, much more thoroughly, and you'll achieve better de-wetting and better removal of that coating. So the buffer and the chelator, really you can think of them as doing two things. First, you're controlling acid-base reactions, which is really important, preventing unintended reactions from occurring. Second is you're helping to clean the surface, which then helps to de-wet the surface. So both of those are really beneficial when working with microemulsions. And you can see here, this has kind of become an infamous piece of pottery at the Arizona State Museum Conservation Laboratory with a very stubborn soil layer on it, which was deposited on it in a house fire. So very complex soot layer that was practically insoluble. And attacking it with just a regular microemulsion didn't do the trick. Attacking it with just regular buffer and chelator solutions didn't do the trick, but combining the two did the trick. And that was actually the only thing we found that was able to solubilize this soot layer. So you can achieve, really powerful cleaning effects, whether it's de-wetting or not, when working with these microemulsions. So you don't have to think of these as just, oh, I want to remove a polymer coating. You can use these for cleaning, a wide variety of surfaces. And I think I've cleaned just about every type of surface with these microemulsions at this point.
Luke,
So
can I interrupt? Can you explain what you mean by de-wetting? It's not a term I'm familiar with.
I think I have a slide later on about de-wetting, and we can get into it in just a couple minutes, but a really brief description of de-wetting is, instead of solubilizing a coating where you're dissolving it and removing it from the object, De-wetting swells the coating and then has it detach from the surface in a semi-solid state. So you're actually detaching the coating from the surface instead of dissolving it. And it actually will, if you achieve full de-wetting, it will curl in on itself and it just, comes right off, as a layer. Or sometimes it'll come off in a partial de-wetting and it looks almost like something like eraser shavings. It's quite interesting. But what's nice about de-wetting as opposed to solubilizing is that you can remove heavily cross-linked coatings that would be impossible to solubilize and remove from a surface. So that's really the big benefit of de-wetting something. So it helps swell it, lifts it off the surface, and then it can be removed. So that's the really brief kind of de-wetting primer, but we can definitely get into that more. That's one of my favorite topics. But so getting back into the buffer and chelator concentrates, which we talked about a little bit earlier, there's one thing that you don't want to do when you're working with microemulsions, and that is mess up the proportions of the materials. So you don't want to disturb the proportion of the solvent to the surfactant. So when we're talking about doing MCP testing, if you were to go about this kind of the standard, following the standard MCP testing protocol, it could be really difficult to make up the test solutions without disturbing those proportions. So by introducing these ultra concentrated buffers and chelators, you can actually start with a standard stock microemulsion, and Chris will get into that later. You can start with a standard stock microemulsion and add 2 to 4 drops of a buffer or chelator to that microemulsion, which will provide the appropriate molarity, which is usually 0.05 molarity. So you're providing the appropriate concentration without really affecting the volume of the solution. So, adding 2 drops of material to a 5 milliliter portion is not going to change the volume enough to disturb the proportion of surfactant to solvent, which is what you want to preserve. So that's really what these buffer and chelator concentrates let you do. It lets you modify the microemulsion tests without disturbing the microemulsion and impacting its performance. So these buffer and chelator concentrates, they're made at 3.125 molarity or 62.5 times concentration, and they're added in a 5 milliliter test 2 drops at a time. So if I wanted to test a microemulsion, I would take 5 milliliters of my microemulsion and put it in a little measuring cup, a little weigh cup. And then if I wanted to test it at pH 8.5, I would take 2 drops of my pH 8.5 buffer and put it in that cup. And if I wanted to add DTPA to it, I would take 2 drops of my DTPA concentrate and add it to that cup. And there you go. Now you have a buffered and chelating solution along with your microemulsion. So we make these in 10 or 20 milliliter portions. 10 milliliters of these concentrates are going to give you 125 microemulsion tests. That's a lot of tests. They don't take up very much space. They're easy to use. They're portable. There are a lot of benefits to using the concentrates, especially if you're a conservator that tends to go out in the field a lot. It's really nice because you could essentially fit the entire MCP test kit in your pocket. Or if you have a small purse, you can literally shove the thing in there with a rubber band around it and you're good to go, and you have everything you would ever need for it. So it really reduces the size of that test kit. And I use that all the time because I work on site, all over the place. One other thing that's really nice about the chelator concentrates is that you can actually add them to any standard pre-prepared microemulsion. So there are actually quite a few companies now that are making pre-prepared microemulsions. Dr. Baglioni's company, his group has these products called NanoRestore. That's the name of the product, NanoRestore Cleaning Systems. So you can actually, if you wanted, you could order those microemulsions and just add these buffers and chelators to those, and they would work perfectly fine. There are a few companies in the United States that also make pre-made microemulsions that are pretty interesting, and we could get into those later if anyone would like. But, making the concentrates is no big deal. We'll go over that in a second. But, here is a 20 milliliters of pH 8.5 bicene concentrate. So you can see the size of the vial. It's really about that big, and you get 125 tests out of that guy. So, very practical, portable, and easy to use. Here's a little video showing a pH 5.5 DTPA chelator. So that's actually, out of all of the concentrates, that's the most difficult one to make. And difficult is kind of in quotes because it's really not difficult at all. Essentially what you do is you add your DTPA and your sodium hydroxide to a mortar or a beaker, and you stir both of those solids around with a little stir rod or a pestle. And if you want, you can kind of grind them together. That's kind of a dry reaction, which if anyone has done organic chemistry recently, that's a really wonderful green chemistry technique to start out by pre-mixing your solids like that. You start the reaction there, and then it dissolves more easily. But so you start out by blending those together and then putting them into your water with your stir bar in it, stirring at about a medium speed, and that's about it. So you measure out your materials, add them to a beaker, mix them up, then add that to water with a magnetic stir, and you're good to go. So this is that material mixing, and it has a viscosity similar to syrup or something like propylene glycol, but you can see it there. It's not too different from a regular MCP concentrate. They're very easy to prepare and easy to work with. One tip that I do have when working with these concentrated buffers and chelators is if you can clamp your beaker or container down on your magnetic stir, that is a really big benefit. It stabilizes that beaker. It will keep it right over the center of that stir, so you get better mixing. And as it starts to dissolve that material, the viscosity increases, so it'll want to kind of kick and move around a little bit. So having that clamp in place is really useful. That's just like a $1 clamp from a Harbor Freight or something like that. But it really makes mixing these up a lot easier. And this is just a little 50 milliliter beaker, which I like to mix these up in. Once you've added all of your DTPA and your sodium hydroxide to the water, another thing that you can do is just cover the top of that and then walk away and let it mix for a bit. So you can cover the top of this with tin foil or plastic wrap or whatever, nothing fancy. You can let it sit there and mix for 5 or 10 minutes, and the whole thing will you'll come back and it'll be a nice homogeneous solution. Let's see. So a lot of people are confused about what these microemulsions actually do, or what they're capable of, or where you might want to use these. So there are some situations where you would use one microemulsion over another. So this is one that is a really nice system that's included in the new modular cleaning program, and it's DDAO DC. So a lot of times you'll have the surfactant name, DDAO, and then the solvent type after that, DC, in this case, diethyl carbonate. You can see this one has, it's at pH 8.5, it has bicene and EDTA in it. And I use this system to remove some dyed lacquer from a Frank Lloyd Wright piece. Something like this DDAO DC mixture is really good for things like Roplex or nitrocellulose lacquers. Works very nicely on that. Another microemulsion that we'll look at later will also work pretty well on this, but some of these are just suited to certain materials a little better than others. Part of the MCP testing protocol and part of these ultra concentrates is that you can make up all of these microemulsions really quickly in a lot of different combinations and test them on whatever surface you're trying to de-wet or clean really efficiently. I can test something like 10 different microemulsion solutions in under 5 minutes. It takes almost no time at all. It's very simple to do once you have all this set up. You can see up here in the top left, this is straight from one of Baglioni's papers, but this is Roplex, or this is a sample where they had Roplex on a fresco where they were testing out this DDAO DC mixture, and you can see how nicely it de-wetted that solution. Stephen, if you look at this, you can see around the edges how it's not actually dissolved, it's kind of lifted and torn apart, and you can see how it's lifting under here. So it literally lifts it up away from the surface and curl in on itself, and you can actually see on the edges here it's curling in, and that's for quite thick polymer layers. It'll work nicely on that. Here on this lacquer, you can see it's a very thin lacquer, and works really nicely on that too. So this is another microemulsion system. This is the SDS, which is sodium dodecyl sulfate, EAPC, which is ethyl acetate, and propylene carbonate. And this is probably kind of the superstar of the new suite of microemulsions. This is a really nice microemulsion system. It works on a wide variety of coatings. It really excels on acrylic coatings, acrylates like Paraloid B72. It works phenomenally well. I've also used this to remove things like shellac and boiled linseed oil, and we'll look at that in a little bit. But this would be kind of like your all-purpose microemulsion. This is probably where you would want to start most of your tests, is with this microemulsion system here. And so everything with a percent by it is the microemulsion system. And then below that are the additives. That's your Bi-C and your sodium hydroxide. So that's that, that buffer and that chelator that you're adding to it. So this system here works really nicely on a wide variety of materials. In this case, on the right-hand side, this is actually a catalyzed lacquer coating. And I use a system very similar to this one to remove that catalyzed lacquer. You can see on the top, there's that very thick lacquer coating, on the bottom, nicely removed. So this is a really good system for a wide variety of materials. So that same system used here, this is on shellac that is well over 100 years old, around 120 years old or so. And one thing that's interesting about shellac, under UV light, it actually fluoresces green after about 100 years or intense light exposure. Most people expect to see orange, but it will actually fluoresce green after a long time. But on the right-hand side, you can see the microemulsion system. And on the left-hand side, you can see just regular ethanol, which is, the go-to if you're coming up against a shellac coating. So on the left, there's that ethanol that was applied to the surface for 30 minutes. And on the right was a pH 7.5 tris and citric acid solution. And it was that SDSEAPC. And that was allowed to dwell on the surface for about 5 minutes and achieve this cleaning result. And essentially what I did here was I applied a small little tab of Evolon CR, which is just a type of cloth. You could use Japanese tissue or even a paper towel if you wanted. Put that on the surface, put a few drops of my microemulsion on there, covered it with plastic and let it sit, and then lifted it up and took a swab and just swiped it off, and it just, lifted off like it was, a sheet of dried lacquer or dried shellac. It just comes right off of the surface. And the other thing is that, what Chris mentioned earlier, the clearance with these systems, since we are using, buffers and chelators, we do want to clear these, and we do want to continue using our pH adjusted waters. And in fact, when using even just a regular Baglioni style system without a buffer or chelator, I would probably clean with at least a neutral pH adjusted water or something, similar to that. So this is another similar piece. This is a plant resin varnish. And this is, from about the 1880s or so. And you can see actually here that varnish has flaked off in several areas. But again, using that same microemulsion system, at this time at pH 8.5 with EDTA, and letting that again dwell for about 5 minutes, you can see how nicely it removed that plant resin varnish in this little test area, which is a weird triangle kind of hat looking thing because I wanted to get a cone on her face, and I happen to have a piece cut like that already. But you can see it can remove these really generally tough to remove coatings very easily. A plant resin varnish that's 140 years old on a surface like this is usually a nightmare to remove. But a microemulsion that's properly buffered and has a nice chelating agent makes short work of it. So this is another interesting thing that you can do with these, and this is an EcoSurf-based microemulsion with Bi-C and DTPA. Here on the upper right-hand side is a layer of boiled linseed oil and shellac. And this system works very nicely with that. So does the SDSEAPC. But you can use this to remove a wide variety of materials. And when you're removing something like this, that's not a standard polymer coating, when you clear this, it actually kind of rolls off the surface like an eraser shaving, like I mentioned earlier. So it doesn't come off as a de-wetted sheet, but it actually kind of rolls off as a solid. It's very interesting. On the left-hand side, you can see this is the Evolon CR applied to the surface and wetted with a microemulsion. And you can see that the material below, the boiled linseed oil and the shellac, is solubilizing and coming up into the Evolon CR. I have that covered with just 5 mil polyethylene sheeting from the hardware store. And once you remove that kind of poultice of the Evolon CR, you can just wipe it off with a cloth, and it will give you this really beautiful surface underneath. And here, I was using a pH adjusted water with isopropanol or propan-2-ol, if you want to use the IPAC name, to clear that surfactant system. So those are really the basics of using these microemulsion systems with the buffers and chelators. That kind of gives you an idea of what they can do and where you would use them. And within the MCP, there are actually some instructions too, which will give you some guidance on what you would use where. So, for example, in the upper right-hand corner, Chris will show you this. It'll tell you this system is good for, acrylic coatings, or this system is better for, something like a lower polarity coating. So there will be some guidance there, as we all kind of adjust to this new microemulsion reality we're living in. So I'll hand it over to Chris for the new MCP version 11.
A couple comments. First of all, Luke and I differ on using solid sodium hydroxide. I think part of it is Luke is in the desert where it doesn't accumulate water like it does in other places. And also it just scares me to have people handling that. So all the solutions in the MCP are based on 50% sodium hydroxide in water. So that's one thing. The clamp holding the jar is great, but works really well is 2 pieces of blue tape. That'll hold a really strong, you can use it on gel systems. It'll really hold it in place well. Let's see. We have to get together on how we name these things. He rattled off some names, and then you'll see my names are about 2 paragraphs long. And one of the things Luke hinted at, but didn't really dwell upon, is that with the de-wetting, it's a very unfamiliar process. Typically, with a de-wetted film, it works better to push it off dry, like with a dry swab, a cloth, than to use a wet swab with the microemulsion on it. That will just kind of collapse the system. The microemulsion runs under the de-wetted material, kind of re-swells it, makes a sticky mess. But just taking a bamboo skewer or something and just pushing it off a flat surface is remarkable. And one person who was using this said that when she brought in assistants, art students or something to work on this project, they were fine with just pushing it off with a dry stick, but all the conservators wanted to dip their swabs in the microemulsion and clear it with that like you would normally. And it didn't work as well for them as the people who were just fine pushing it off dry. So, okay, let me share my screen.
And while Chris is sharing his screen, I'll throw in there too, it's really nice to use that dry swab when you have a really good de-wetting result. Sometimes, and we can talk about this later, sometimes you'll get what's called partial de-wetting, where the entire system does, or the entire coating doesn't de-wet. And there are some tricks that you can use for that, like using, a mineral spirit or, a silicone-based or a silicone solvent to remove that, but we can get into that later.
Okay, so this is the familiar part of the MCP. Let me start by showing some of the new solutions. What I've done is I've flagged the ultra concentrates. We're going to refer to Luke's 62.5 concentrated working solution as ultra concentrates. And those are denoted with a little double dagger like you use in a footnote. So here we have the citric acid sodium hydroxide. You'll see it's 62.5 times the working concentration. The working concentration is still the same as always. We're going to make 10 mils, and it's kind of amazing. We're going to put 6 grams of citric acid and 7 grams or 4.95 mils of sodium hydroxide. Mix those together, bring the volume up close to 10 mils, and then check the pH and adjust as necessary. So far, the mix it button doesn't work, but by the time it's released, it will. It'll give the correct directions. The other interesting thing is now we have microemulsions. These are the stock microemulsions Luke was talking about. So here are the ones we have in already. And when we click on them, we get this page, which is a bit daunting. But here is the microemulsions. This is the percentage. Remember, microemulsions are based on weight. So the weight percent, it's 65.9% water by weight. So it's, 2/3 water to start with. And so we're working in this modified aqueous system. 3.3% of a surfactant barrel, which this was published recently in one of Baglioni's papers. And he says it's for PVAC resin coatings. We have two surfactants, the sodium dodecyl sulfate and the beryl. As a co-surfactant, he's using N-butanol, and methyl ethyl ketone is that solvent that's dispersed into the micelles. One of the interesting things is you'll notice that most of these solvents have solubility in water as well as being hydrophobic. They don't want to be in water. So these, they're not generally true microemulsions, or they're modified microemulsions where that solvent kind of moves in and out of the micelle. And this is what gives it its special interesting properties for de-wetting. And over here, there are just a bunch of numbers to let you know what the molar ratios are and all that sort of thing. And if there were any azeotropes in those solvent systems, they would be listed here as usual in the MCP. And then here, I'm calculating the Hildebrand and Hansen solubility parameters, but that applies only to the pure solvent. Once it's put into an emulsion, all bets are off, but I thought, hey, I've got it calculated, I'll show it off. So these are very simple to build. This is one Luke sent over earlier today. You're gonna create an oil and water emulsion, and it's the microemulsion. And we're going to use 4.1% of sodium dodecyl sulfate. And you'll notice both sodium lauryl sulfate and sodium dodecyl sulfate are listed. Sodium lauryl sulfate is mostly sodium dodecyl sulfate, but for these systems, we want to use pure sodium dodecyl sulfate. So you have to buy that from the supplier. So here's our sodium dodecyl sulfate. We're going to use a co-surfactant of N-pentanol, which is under the P's. And we'll be using that at 7.9%. And our solvent is going to be xylene. And we're going to use that at 2.6%. And you can see the program says, okay, we know it's at 85.4% water. That matches the recipe, so we know we're good on that count. And that's all there is to it. To mix it, you would put the sodium dodecyl sulfate into your water, dissolve it, add the N-pentanol, and then the xylene. One of the tricks that Luke has mentioned is you don't want to stir vigorously. You want to do kind of a gentle stirring. So a stir bar, slow rotation, but not foaming and frothing, and then add the solvent slowly, dropwise. Okay, so we've built our new, we want to say it's a microemulsion. So, okay, so we've got a new microemulsion. Let's put it into a solution set. And this is where things get a little confusing. And well, I apologize, but there are going to be basically two ways to work with these microemulsions in the MCP. One is if you have the ultra concentrates that Luke's made, and you've made a whole set for yourself, we can work with stock microemulsion solutions that we just modify the pH with those small amounts of the ultra concentrated solutions. The other way is if you have a standard MCP set, you build the microemulsion from the MCP concentrates. So let's look at what Luke described already, the ultra concentrated microemulsion. So we're going to edit that. And here is our information page. And we're going to add our new microemulsion to the list of the ones in our kit. Here are the pH buffers we're going to use, 5.5, 6.5, 7.5, 8.5. And you'll notice they all have that double dagger in front indicating they're ultra concentrated. We have our ultra concentrated chelators, citrate, EDTA, and DTPA to make up our set. We've picked some solvents to use as co-solvents. So we can then tweak, once we've got everything mixed up, we can tweak by adding maybe 1 or 2 drops of butanol or benzyl alcohol or xylene. And we have our familiar adjusted water rinse systems. So we've added that to Luke's ultra concentrated microemulsion recipe. So how are we going to use this? We will start begin a cleaning test. We're going to use an emulsion. And now in the MCP, we have 4 variations. We can do a nanostructured fluid microemulsion, which is what we've been talking about. We can also do the pamulin or xanthan stabilized convention solvent in water. We can make a silicone gel emulsion with something like KSG 350Z. And we can use the phase diagrams for the water and oil microemulsions. So we're going to do the nanostructured Baglione style microemulsion. Here's our familiar first page of the MCP. We're now in the emulsion world, and we have 2 stock systems. We have our ultra concentrated microemulsions and the standard microemulsions. So let's do the ultra concentrated. And just like always, we're going to start a cleaning test. And the first thing we want to know is how big a little cup we want to use, so whether we want to do a 10 milliliter vial or a 5 milliliter vial. So let's do 5 milliliters. So we can pick which microemulsion we want to work with. And in no particular reason, we're going to just pick this one, 85.4% water. So we want to modify that. Again, the standard methodology for using the MCP, you either use it or modify it, or it's not working at all. So let's add a buffer. So here we're going to add, with our micropipette or carefully measured how many drops our standard pipette is, we're going to add 46 microliters of the 5.5 ultra concentrated buffer. We can modify that by adding a chelator. And here we'll be adding 0.0633 grams or 67 microliters of our ultra concentrated citric acid. And at each point we can test this. For the time being, ignore all this down here. And the way we would mix this is to take 85.4 mils of our stock. We would take 5 mils of our stock solution that we've made in the bottle, make like 100 mils of our stock microemulsion solution, and add the 46 microliters using our auto pipette of the MES buffer and 60 something microliters of the citric acid ultra concentrate. And we would have our test solution, just like we're familiar with. It's as easy as that. So let's talk about the other way to approach this, and that's the non-ultra concentrated microemulsions. This is where you have the standard MCP kit like what I have. I haven't made the ultra concentrates myself yet. So we have our standard microemulsion. We're going to edit it so we can put in that new microemulsion we just added. So we can scooch that over into our set. And in this case, these aren't bottles of stuff we've pre-mixed. These are the concept, the recipe we're going to follow. So again, our 4 different buffers, 3 different chelating agents at each pH. Again, our co-solvents, if we want to add that, and our clearing agents. So let's do a test with this. So we're going to begin a cleaning test. Again, click on emulsion, nanostructured. This time we'll use Luke's standard microemulsion and start a cleaning test. And again, we'll do 5 mils. So like the familiar MCP, we're going to do 5 mils in our little cup. So first, we could mix this up by taking 3.67 grams or mils of water, adding 0.19 grams of sodium dodecyl sulfate, 0.35 grams of N-pentanol, 0.4 grams of ethyl acetate, and 0.4 grams of propylene carbonate. That's going to make our base microemulsion if we want to try it without any pH adjustment or chelator present. And that's basically what you premix in the jar the other way. But we can modify that. We can, yes, but modify. We can add a chelator or a pH buffer. Let's add a pH buffer. So now what it's saying is with our stock, our old-fashioned stock our old-fashioned stock MCP solutions, we take 0.733 grams or 0.733 mils of our pH 5.0 MES sodium hydroxide 10% stock solution. This is what we've been making for years, excuse me. To make this microemulsion, we start with 2.93 grams mils of water, add our 0.733 grams of our concentrate, or normal 5 times concentrated MES buffer. And then to that, we add our sodium dodecyl sulfate, stir until it's dissolved, and add our co-surfactant and solvents, again, stirring slowly, using a magnetic stirrer slowly, and add that. And while we've never tried this, every expectation is this will make your microemulsion fast and easy as well. Not as fast and easy as having the ultra concentrates and the pre-mixed stock microemulsions, but it should be pretty quick. And it means you don't have to make 16 new bottles of ultra concentrates. So that's pretty much what I've been doing for the last few weeks and intensively for the last 3 days, modifying the MCP to let us do all that. I think let's open it up for questions and discussion. Let's stop the share.
So I think the first thing is that, to make a few distinctions, because the most confusing part about this is just the software aspect. So there's a difference between testing with the microemulsions and the ultra concentrates, and then making your bulk solution that you're actually going to use. So the methodology is you start by testing your microemulsion systems. You select whichever one that works best, just as you normally would with the modular cleaning program. And once you've selected it, then you would go through and build a larger solution based on that test for the actual de-wetting. So for example, if I were to go and redo that catalyzed lacquer tabletop that's 5 feet long by 2.5 feet wide, 5 milliliters isn't going to cut it. But if I did a small test in the corner and I found that the SDS EAPC microemulsion with pH 8.5 bicene and a DTPA chelator worked really nicely on it, then I could use that to build, a 100 milliliter solution or 200 mils or however much I'd like, and then that could be applied to the entire surface. So you still have the same testing phase, and then you have the phase where you build your bulk solution based on your test. So that's still, exactly the same.
The yes clean button, where it will ask you how much you want to make and give you the recipe. Guess what doesn't work yet? But as I said in the email, it could be vaporware, which it's not. It could be alpha testing, beta testing, or just the usual buggy program. And we're in beta testing, alpha testing right now. So Luke and Stephen are going to get copies to play with and tell me all the things that aren't working right.
Well, so far things are working pretty well, but all this stuff is not too difficult to use. The other thing is, another distinction to make is that with the ultra concentrated solutions, you're using stock solutions of the microemulsions. So what that means is you take your regular microemulsion at 1 times concentration. It's just your regular microemulsion. There's nothing concentrated about it. And you make up about 100 milliliters of that, and that's your stock microemulsion solution. and that should probably last you several lifetimes, unless you do, a huge amount of, coating removals. But so you'll have about 100 milliliters of a stock microemulsion in a bottle. You'll take a 5 milliliter aliquot of that and put it into a weigh cup for your test. So I go to my stock solution that has my microemulsion in it. I take 5 milliliters from that, I put it in a little weigh cup. And then from there, that's when I go to my ultra concentrates and I add 2 drops of my pH buffer or 2 drops of my chelator. And I can do my test that way. Now, so when you're doing this the other way, kind of the standard MCP way with the 5 times concentrated solution, when you do that, you have to rebuild the microemulsion every time you do a test. So you have to add your surfactant and your solvent to that little 5 milliliter test every single time. Whereas with the ultra concentrated system, you already have that microemulsion made up and you don't have to worry about adding, a few drops of solvent or a few drops of surfactant. All you're doing is adding a few drops of buffer and chelator. So you can tell which one I'm partial to, but it works really nicely and you can test things really quickly. So go ahead.
Finish up. I didn't mean to interrupt.
Oh, it's okay. So if what you can do is if you wanted to test multiple pH ranges on an object, you could actually take 4 little weigh cups and put 5 milliliters in each weigh cup from your stock solution bottle. Or if you want to get wild, you could put 2.5 milliliters in each cup. And then you could add 1 drop of your buffer or 1 drop of your chelator to each one of those cups, which is actually, that's normally what I do. But so you can do 5 milliliters in each cup of your stock microemulsion, pH 5.5, 6.5, 7.5, 8.5, and then do a test. And then you can add your chelator to each one of those. So if you think you need really strong chelation, you can add DTPA right to that cup, and you don't actually have to remix the whole thing. So you kind of have this nice, cascade of tests that you can do really quickly and efficiently. So you can test 3 things really fast. And if you're testing each pH range, you're going 4, 8, 12 tests, and you can do that in a matter of a few minutes. So it really, speeds up the process of doing these tests with these microemulsions, if that makes sense. If I didn't explain that well, let me know.
You did.
But, okay.
And the other thing to point out is, well, first of all, the new MCP workshops will be making the ultra concentrates. And the other thing is you can use the ultra concentrates just like the regular MCP, but instead of 1 mil, 1 mil, 1 mil, 1 mil equals 5 mils, you take 5 mils of distilled deionized water and add your 1 drop, 2 drops of the MCP concentrates. It'll actually be a little bit more complicated because if you want to add a surfactant, that won't be concentrated that way. So you'll have to, but the MCP will walk you through it. And if you want to use a stock gel concentrate, you'll be using 1 mil of that and then add a proportional amount of water and then the 1 or 2 drops of the ultra concentrates. So that's all going to be incorporated into the new MCP. So it's not like you have to make up the old 100 milliliter 5 times concentrates and the new 62.5 concentrateds 10 mils in the little vial. So it'll be one or the other.
Right. So I've just completely switched over to the 62.5 time concentrates. So even when I'm building just a standard MCP solution, no microemulsion involved at all, I'm using the 62.5 time concentrates, because what I'll do is just then take 5 milliliters of water in a weigh cup, and I can add in 2 drops of Bicene or 2 drops of a chelator and go through there and do my testing just that way for a regular aqueous test. So you can use the concentrates everywhere. It's not just just for the microemulsion. The other thing that's nice is if you're like me and you don't have your laptop or something with you everywhere, if you're out in the field, you can do all of this in your head really easily. And you pretty much always have access to water. So as long as you have your concentrates with you, you can do all of these tests really easily in the field and just in your head. So if you have 5 milliliters of water that you can measure out with a pipette, and then you can then dip your pipette into your buffer and chelator and add 2 drops in each of those, you can just do all of that with pen and paper, and you don't even have to open up the program if you'd like. So it makes it very easy to do all of this stuff just in your head. There's not really, any complex math involved.
Luke, when you said you make up 100 milliliters of your stock emulsion, and you said it would last a lifetime,
Mhm.
Is that just a lifetime of testing, or do you use it in such small quantities in the application that will also last you a lifetime of treatments?
Well, that's just for the testing. So that's just your
Okay.
testing solution. Just like how your MCP 5 times concentrates are just for the testing. You wouldn't take your 5-time concentrate to make, 5 gallons of a solution or something. So that's just, purely for the testing. And if you get, kind of more restrictive with your materials, you can really just do those 2.5 milliliter tests and extend that even further. So now you're talking about, 250 tests per, set. That's a huge amount of testing that you get out of these little kits.
I've got a question. Basically, the difference between a co-solvent, the standard co-solvents that we've been using, the N-butanol and the whatever. And how is that co-solvent a different situation than a microemulsion solvent? Because they're both, you're both adding a certain smaller amount of solvent. Does that mean that those old co-solvents were sort of acting slightly like a microemulsion, or is there some sort of cutoff that makes the co-solvent different than the microemulsion solvent?
We're using two terms to describe the same thing. You're talking about co-solvent, and we're going to use that in terms of microemulsions as something that you add extra. So you've got a microemulsion that you like, you might want to try adding 1 drop of something. So if you need more aromaticity, you could add a drop of xylene. That'll just go into that microemulsion and modify it slightly. That's a co-solvent. The co-surfactant, which is the same chemical generally, so it's normally straight chain alcohols, long straight chain alcohols, so pentanol, butanol, hexanol. Those are added and they form part of the micelle. So the standard picture of this kind of microemulsion is you have your micelle, and the normal thing is there's 1 surfactant molecule and 2 co-surfactants, these long chain alcohols per surfactant molecule. So you form this more squishy micelle, and it helps bridge. Remember, a microemulsion is thermodynamically stable. So you're really working very hard to take water and your oil and make them, the surface of those two where they come together, thermodynamically compatible. So the alcohol has a lot to do with that happening, because remember, alcohols are actually very low HLB surfactants. So we're using a high HLB surfactant and then adding in the co-surfactant as a low HLB surfactant. So we're doing all sorts of things at the same time with this co-surfactant idea that's distinct from a co-solvent.
Okay, I guess I wasn't seeing the alcohols as being surfactants. I understand that they, have those wetting effects and that they, do help pull. If you put a little bit of an alcohol into water, that it will help, solubilize things. But I'm still, a really old, early on sort of Wolber school, thing where, I'm looking at benzyl alcohol and butanol as these things that you add as solvents that you add in to an otherwise aqueous solution. With things like chelators and surfactants and pH adjusted, and you add a little bit of solvent. So say benzyl alcohol. I mean, I think that was one of Richard's favorites. He threw a little bit of benzyl alcohol and everything. I go, well, that's, of course, because that stuff is really strong. These microemulsions, is it that you're not making a microemulsion that's 60% water and 40% benzyl alcohol?
No.
I mean,
no. So it's a little different in this. So the way that you use a co-solvent in this system, really the only time you're adding a co-solvent in the microemulsion world is when you want to play with aromaticity. So you're not adding it for other solvent effects like you might want to. So, say a coating is more soluble in this particular solvent, so you add that to your solution. That's not the game we're playing. If you're adding a co-solvent in the microemulsion system, you're really playing with two things. One is aromaticity, and the other is basically adding an aliphatic hydrocarbon of some kind. So you're playing kind of an affinity game, more so. But I would actually steer clear from benzyl alcohol right now. I need to do more research into this, but the benzyl alcohol actually has some interesting effects on the micelles that can help or hinder certain microemulsions in certain situations. So for the microemulsion world, when you're adding co-solvents, you're talking about adding, maybe 0.5 weight% of xylenes if you want to add aromaticity, or something like 0.5 weight% shell saw D38 or mineral spirits to add some of that aliphatic hydrocarbon, which is, again, a little bit more of that affinity game to help induce swelling of that substrate or that polymer a little more. So it's a little bit of a different of an idea. I do think your question though earlier about how this is different and how, were you just forming kind of like small microemulsion systems before if you built an aqueous solution that had buffer, chelator, surfactant, and then you add your co-solvent in. So you were kind of building a little bit of a microemulsion there. The difference is that it's not as effective as a microemulsion. So these microemulsion recipes that you're getting in MCP are highly effective microemulsions that are essentially, tuned on a level that looks at, energy and kinetics and other things. So prior to this, when you're building that aqueous solution, you would add that little bit of solvent and you had a surfactant in there. Sure, that surfactant would probably incorporate some of that solvent into the micelle, but it's not really performing like a microemulsion that we're talking about. It's a difference in performance more so than a difference in chemical composition.
Well, I was wondering too, if you use as Mark was saying, if you use the benzyl alcohol as a co-solvent in more traditional aqueous cleaning systems, until you start adding large amounts of some organic or non-polar component, it's not inclined to form micelles, is it?
Once you're above the one-time CMC concentration of a surfactant, you are forming micelles in that solution.
But now you're talking about a solution that has a surfactant in it.
Right, it's all about the surfactant.
Yeah.
Yep. If you're adding a solvent to your solution with no surfactant, that just means that solvent can be mixed in some proportion with water, and it's just incorporated, homogeneously into that mixture. When you add the surfactant into the solution, as long as it's above the 1 times critical micelle concentration, when you add a solvent in there, if it's not miscible, so like something other than like acetone. So say you have acetone, which is, 100% miscible with water. It mixes completely. You don't need to do anything. That's not going to make a microemulsion. But if you add some xylenes to that, that's totally hydrophobic. That's going to go straight into the micelle. And that's going to go inside of that hydrophobic core of that micelle. And at that point, you have micelles that are filled with solvent. When you have just a surfactant in the system with no solvent, you still have micelles, but they're just small, very small micelles that just consist only of the surfactant. And the interior of that micelle is basically that long, usually, aliphatic tail with no solvent. So maybe we should go to the chat for a few questions. Susie asked if you need a bubbler for these. You should not need a bubbler or any special equipment for a true microemulsion. There are a lot of different types of things that are similar to microemulsions, but microemulsions should form easily and spontaneously. Like Chris said, there are some formulation tricks that make them form better. And those tips are things like don't destroy the thing while you're working with it, don't shake it like a monster. If you're gentle with it and you mix it, it should form just fine. So one thing to think about is if you're mixing something with a huge amount of torque or really high, you can actually start to damage molecules in the system. That's not a rigorous way of saying it, but that's essentially what you can be doing with some of these surfactant systems. So just using gentle mixing, that's really as complex as the mixing with these is. So you shouldn't need a bubbler or anything like that. When you're talking about using specialized equipment, you're getting more into the range of things like mini emulsions or things like oil and water in oil emulsions and things like that are not what we're talking about. So if you have a container and something you can swirl the stuff in, then you should be able to make all these microemulsions. And then Michael asks if solvents are added separately or mixed together. So the standard routine that you want to follow when you're making these is one, if you're building the actual solution, not the test, what you do is you make up your aqueous components. So you make your you make up your buffer and your chelator, and you test your pH. From there, you add your surfactant, and from there you add your solvents. And you can add the solvents one at a time or all together in a blend. That doesn't matter. So that's totally fine. Co-surfactant can go in with the surfactant or in with the solvents, because the co-surfactant is almost always a long chain alcohol and it doesn't make a difference. So when you're making the actual solutions, it goes aqueous system first, check the pH, add your surfactant, then solvents. And you can add those solvents in any order you like. One thing that you'll find that will be kind of interesting is that with some systems, the microemulsion won't actually form until all the solvents are in there. So it might look kind of cloudy and hazy for a bit, and then you add your final solvent and then it'll all of a sudden go clear. And that's what you want. That translucency is what you're looking for. So hopefully that answered it.
Do brushes work as well as dry swabs for picking up your de-wetted films? Yeah, because I see that they might have some advantage in getting those little bristles underneath your partially detached material.
Yep. Yeah. Brushes work nicely. Even scalpels can work nicely. It depends on the level of de-wetting that you get. So one of the things about working with these practically, when you read all of these papers, these systems are designed usually for a particular coating and an ideal setting, and they're de-wetting these things on, slides. So it's usually not, a real world, setting where you're getting complete and total de-wetting. You're usually getting like some kind of gradient of de-wetting. So, in some situations, you might literally be able to pick it up with your fingers. It might come off when you peel off your gel or peel off your Evalon or your tissue paper, or you might need to get, a scalpel blade and slip it underneath that and peel it off that way. So there are different levels of de-wetting that you get. It's not just, one type where it just rolls off.
And I would think with a brush, if you were to angle it rather than stroking, to angle like a stiffer brush.
Exactly. Get under there with a little bristle brush. Yep.
Yeah.
Someone asked why 62.5. That's the concentration at which, if you have a regular pipette that has 25 drops per milliliter, or if you don't have an auto pipette or a nice scale, you can still build these systems by just using 2 drops from that 25 drop per mil pipette, and that's the concentration that correlates to that for most of these materials. So that's really where it came from. And that's also right around the 3 molarity concentration, which is about as concentrated as you can get with these things and still have decent working properties. So that's really, where that came from. Nothing super complex. If you want any higher concentration, it would be like working with honey or something. It would be way too viscous.
The MCP takes the calculations a little bit further,
right?
Where Luke's is saying, if you have a stock microemulsion, that you have 5 mils of that. He's assuming his concentration is based on it being 100% water, and the MCP actually calculates what percent water is in that microemulsion and tells you to add the corresponding amount. I don't know if there's a real difference there, but that's why the micropipetter may prove. I haven't used it yet for the system, but you just dial in the amount you want. You have a bag of tips and you're good to go. This was something like $29. The tips were a bit more. The other thing, green wise, if you do throw things away, this is all you're throwing away compared to a regular squeezy pipette. So a lot less plastic waste if you don't save them and rewash them.
Yeah, and that is an interesting topic when you're talking about water versus other solvents and solubility. of your chelators and buffers in those systems. What I've kind of found is that with a lot of the solvents that you're using in these microemulsion systems, they're quite soluble in water. So something like propylene carbonate is 20 to 22% soluble in water by weight, within 20 to 25 degrees Celsius. So your buffer and chelator is slightly soluble in that propylene carbonate to some degree. And some of that propylene carbonate, maybe half or more of it, is in the bulk aqueous solution. So if you're just going by drops and you're adding in, 2 drops of that buffer or 2 drops of that chelator, you're really not probably getting an effect that's much greater than if you're going by the ultra precise measurement, so you don't need to sweat it that much. So that buffer or chelator is still soluble to some degree in most of those solvents, aside from, the purely, hydrocarbon solvents, when you're talking about xylenes or something like that. And in those cases, when you have something like xylenes, it's usually on the order of like 2 to 3%. So you really don't have that much of the xylenes in there. So you have a high proportion of water in that system. At the end of the day, though, it really doesn't make that big of a difference. So you don't have to sweat it. It's get about the right amount in there, and you'll be okay. Okay, someone asked, does the 18 gauge needle help disperse the solvent in a microdrop form, and the aqueous solution can use a different gauge needle, or is the dispersion in microdrop form achieved through mixing process? So the needle and the syringe are as simple as they help prevent you from spilling solvents everywhere. And when you get one of these formulas from the MCP, it'll tell you how much solvent you need in there. So if it tells you need 8 milliliters of propylene carbonate, it makes it really easy to withdraw 8 milliliters of propylene carbonate into that syringe, and then weigh that on your weigh cup so that you can control how much you're putting in that weigh cup with the syringe, so you can measure exactly how much solvent is going in there. So it gives you a lot of control in measuring. There's really no micro drop kind of consideration when you're just dealing with the pure solvent. I think you're kind of thinking of like a bulk emulsion when you're talking about micro drops like that. But the syringe is really just really nice for handling. And if you're like me and you work from your private studio a lot, what's also nice is if you have a syringe for each one of these solvents, and there's really only 4 or 5 of these that you're generally going to use, you can then squirt your solvent back in the bottle, and you don't have to worry about contamination or wasting solvents too. So you're withdrawing it into a clean pipette, dispersing what you need, and then putting the rest back into the solvent container. You're not wasting a bunch of solvents. So it's just an all around good system to use just for handling. That's really it.
With conventional emulsions, particularly with the KSG systems where you're putting water into the silicone-based KSG, it is really nice to push it through an 18 gauge needle with a syringe, and it will make that emulsion much, much finer. So typically I'll run it back and forth twice through a long 18 gauge needle from one syringe to another, and it really makes a huge difference in the quality of that emulsion. But that's a conventional emulsion, not a microemulsion.
Yeah. And then the other question I forgot to answer was, can you use a different gauge needle? I wouldn't go any larger than 18 gauge, because then your solvent starts to drip out while you're working with it. So if you have, like a 16 gauge or lower, as soon as you start to move that syringe, the solvent is literally going to start pouring out of it. And you can use a 21 gauge, that works pretty nicely, but anything above that, then it gets really hard to withdraw the solvent into the syringe and disperse it. And then when you do disperse it, it's such a small amount, it kind of tends to spray when you do that. So 18 or 21 is kind of where you want to stick for that, just from a handling perspective.
And also make sure you're using a lure lock type needle and syringe, because you don't want this needle popping off. And also get a blunted needle, not the sharp needles. They sell those on Amazon.
Or if you want to go to your local veterinary supply store, you can get a nice 8-inch long 18 gauge needle for a few cents. Well, does everybody feel comfortable and ready to start working with microemulsions? Would everyone be able to go into the studio right now and build one of these systems and use it, or does anybody have any questions that is anyone even interested in using one of these systems is maybe the better question.
Oh, absolutely. Chris, what's the volume of your micropipetter?
It's a 10 to 100. So it's right in the range that we're seeing the numbers generated for the 5 or 10 mil cups.
Well, maybe we can talk about application and how you actually test with these. So if you're going to test with these microemulsion systems, there are a couple of different ways that you can go about it. If you build a little 5 milliliter test, you can test it with something like a piece of cloth, like Evolon CR or paper towel or Japanese tissue. So you can put your cloth on your object and then take 2 or 3 drops and put it onto that cloth and then cover it with plastic and let it sit for several minutes. You know, somewhere between 2 and 5 minutes is the range that I start out with. And then you can check to see if your coating is swollen and ready to come off. And if not, you can let it sit for longer. Another thing that you can do, especially with, you know, your little 5 milliliter test, what I've started to do is I have these little 10 milliliter vials, and I'll put the 5 milliliter test in the 10 milliliter vial. And if I take a little piece of my agarose, that's like a 2 milliliter sheet of agarose, I can drop that little piece inside of the 10 milliliter vial with a microemulsion and let that hang out overnight. And then when I come back the next day, I can take out that piece of agarose and put it on the object and do my test that way. So one thing that you can do with these microemulsion tests is actually save your test. Because normally if you're testing with, you know, a piece of cloth or something like that, you really only need about 3 drops of that to perform your test, and you're making something like 5 milliliters. So if you make a microemulsion, let's say you do your sodium didecyl sulfate with propylene carbonate and ethyl acetate, and you have it at a particular pH and with a particular chelator, you can take that, put it into a vial, label it, and now you can go back to that vial every time you want to test that particular solution. So if you test something with a paper towel or Evolon or Japanese tissue, you can get 25, 50, 75, 8, almost 100 tests out of that if you're doing just drop-wise on Evolon or something like that. Or if you can also then use that to soak multiple pieces of gel. You can keep going back and soaking your gels in that until it's basically gone. So that's another really nice way you can work with these systems. So then you're not rebuilding these over and over and over again. And those little 10 milliliter vials are so small. I mean, you can have 1 million of those things in your cabinet and they don't take up any space. So that's one of the nice practical applications. Then the other thing that we kind of hinted at is that clearance can be a little different with these. And we said that if you have total dewetting versus partial dewetting, you can approach clearance differently. So with the coatings that I normally work with in furniture, they're usually horrible coatings to work with. You know, polyurethanes, catalyzed lacquers, you know, things like that. They're awful. And so most of the time with these that are highly cross-linked coatings, you're only going to achieve partial dewetting. Take even something like boiled linseed oil that has, you know, something like a cobalt dryer in there that's coordinating all of those molecules together and forming cross links. You can use one of these systems for those, but you're not going to get total dewetting on something like that. You'll get the partial dewetting. So you can approach the clearance after you've lifted that coating in a couple different ways. You can start like what Chris said and just go in with a dry swab and try to remove it. You can also just go in with a regular bamboo skewer, just use the skewer itself and remove it. You can try to use a scalpel to remove it. The other way you can go about it is by taking your scalpel or your swab or whatever and dipping it in something like a mineral spirit, Shelsol D38 or Gamsol, or something like cyclomethicone D5, and then going after the coating. And if you've achieved partial dewetting, that cyclomethicone D5 or that mineral spirit can lubricate the surface underneath that coating and help it lift off more easily and reduce abrasion. So that's a really nice trick that I use a lot. And, you know, I've worked on huge surfaces doing that, and it makes it really much easier to remove the coating, and then also reduces the amount of abrasion to the surface. So that's one for just removing that. So with these, I kind of think of clearance in 2 steps. One is removing that coating. The second part of the clearance is removing any surfactant, chelator, or buffer residue. So for that, you can do a couple different things. You can go at it with just a pH adjusted water and clear it to make sure that there are no solids left behind. Or you can actually go with a mixture of an alcohol and water, pH adjusted water. And that little bit of alcohol will help remove any surfactant that might have been left behind. So often when working on wooden surfaces, I use a 50-50 blend of isopropanol and pH adjusted water. And that's what I use for my clearance mixture. And it works really nicely. And you might actually notice that when you do that clearance with alcohol, you get a much better cleaning effect in the end anyways. And it can remove some extra grime and things like that. And then after that, you can either leave it there or come back with just pure pH adjusted water and clear again. So you can clear a couple different times with a couple different things. Now, the last thing you can do, if that isn't, if you're still not satisfied with that, you can come back with something like Shell Sol D38 or mineral spirit at the very end. And if there is any, iota of non-ionic surfactant or something like that left in the surface, it'll come out with that, that hydrocarbon solvent. So you can approach clearance in, several different ways. Go ahead.
Oh, I just had a clearance experience that doesn't have anything to do with artifacts necessarily, but classic paint stripper, from the hardware store. I was actually reading the instructions on the thing after all these years, and it says, clear it with mineral spirits. And I'm like, well, that doesn't make any sense because, it's this weird gel that's water, soluble or whatever, miscible. And, but I tried it on something, some piece of painted wood. And it was amazing using mineral spirits to clear this gunky, hardened gel full of paint curls. And the mineral spirits it did this same thing. It basically made the partially hardened paint stripper full of junk that had come off the surface sort of ball up, and because it wasn't really soluble in the mineral spirits, but it made it kind of turn into like eraser crumbs and gummy balls that wiped off the surface and left the surface of the wood really nice. I mean,
right, and that's pretty common with those regular commercial strippers, and that clearance system using a mineral spirit or something like that. A lot of times when you're clearing with a mineral spirit with a regular paint stripper or something, it's really working more through dispersion and those kind of like physical interactions, those intermolecular interactions, things like Van der Waals interactions and things like that, to physically move things off the surface and provide lubrication and that type of thing. So, you can also think about the fact that once you've dissolved a coating, which is what those are usually doing, that coating is usually, quite hydrophobic. So something like a hydrocarbon will work really nicely to remove it, from the surface.
And it worked better because if you use a solvent like water that will partially resolubilize your gel, then you end up with sort of diluted junk that gets rubbed back in to your surface.
Right, and that's kind of what Chris mentioned earlier, talking about going back in with a microemulsion. If you try to clear again with that same system, it's just going to, make it again a sticky, gunky mess. So you want to tend to avoid that. And we did get another question asking if microemulsions have a shelf life. So no, microemulsions don't have a shelf life, and that's one of the interesting things about them is that they're thermodynamically stable. And if you have a chelator in there, especially, it will last an incredibly long time. I have some microemulsions that have been in my cabinet now for coming up on a year and a half. One thing, if you want to store microemulsions long term, if you want to keep them in the fridge or keep them cool, that can help to some degree. But really, microemulsions should be fine until you've used it all up. There's really no shelf life for these stuffs. Or these things, and the ultra concentrates also do not have a shelf life. The ultra concentrates have so much material in them, they will kill any bacteria on contact. So the microemulsion ultra concentrates will stay for a really long time.
I would add that probably the biggest key to these storage issues is a good cap or lid. If you can get Teflon lids, you're way ahead of the game. If you have a paper liner, you'll probably lose over long term. You'll lose, water will start evaporating out of the container. So it comes down to a good lid. But other than that, they are incredibly shelf stable.
I'm going to put into the chat right now my favorite little 20 milliliter vial, which is from a company I revile, which is Amazon, but they're $1.35 and they're Teflon coated lids. And these are really nice. So they're 20 milliliter capacity. So if you put 10 mils in, it's about half full, which is normally what you should be doing when you have long-term storage for solutions. You don't want to fill that container all the way up to the top. But so these little vials work really nicely for this, and they can have those nice PTFE liners, and you can store a ton of these in your cabinet, and they don't take up much room at all.
Are you going to put up a screenshot?
I just put it in the chat, so hopefully you guys can see that and even click on it. The other thing, especially with the microemulsions, so the microemulsion stock solutions, Chris and I are kind of testing it right now, how they do in polyethylene bottles. I've been storing them in polyethylene bottles for about 2 weeks so far, and they seem to be okay. They don't seem to be interacting with the high density polyethylene. But I actually tend to store these in just glass containers. So I have 200 milliliter glass containers that I store my microemulsion stock solutions in. But if you want to just use the HDPE, containers, that's probably okay. I haven't seen any negative effects from that at this point.
And Bagley only ships his systems in plastic, so.
Right.
I think we're winding down. Remember, we'll repost Luke's materials list and we'll add the vials to it. And if you're not part of we'll post it on the Modular Cleaning Program and Practice Facebook page. And if you want otherwise, send me an email and I'll give you a heads up when the next version is ready and send you that list.
Great.
I think I might also, when we post this video on the AIC forums, I'll probably include a link to the PDF for that, because that has all the materials you need. And any private conservator in North America can order all of these materials without having any kind of, special Sigma Aldrich account or anything like that. You can get all of this stuff, just online very easily. So there's no, barrier between you and making these systems if you want to make them. You don't have to set up a Sigma account to do it. I think maybe the only other tip I would give, unless anyone has any other questions, is to get a little bit of Evolon CR, microfilament textile, and you can get that from Talus or other companies like that. And that material is really nice for a couple different reasons. It holds on to that liquid for a long time. It keeps it from dispersing over a surface, and it also helps pull material up into it. So especially when you're using these systems that have buffers and chelators and you're solubilizing more grime on a surface, it helps pull that up and away from the surface. And the microemulsion seems to, in some cases, have an even better effect than with a gel, because you're literally removing that dirt from the surface up into the cloth. And then it's just the microemulsion versus whatever polymer coating you have. And it can, attack it as it pleases without having to deal with those soiling materials as much. So that's one material I really like and, kind of tend to rely on, and it's not very expensive.
I'm going to give a tip. Apropos of your suggestion of having a syringe for each of your solvents, I tape a little portion of a drinking straw to the side of all of my jars for the MCP solutions and for various solvents that I use around the studio.
That's so old school.
Keep a micro pipette for each of them, so you minimize the possibility of cross-contamination, and you always have a pipette handy for each solution you're going to use.
And if you want to get really wild, on Amazon, you can look up glass syringes. And those are the absolute best for solvents like propylene carbonate or, cyclohexanone, things like that, that really wreak havoc on plastics. If you've ever used cyclohexanone, you know that if you withdraw that into a plastic syringe, the syringe will literally melt and crumble in on itself by the time, you're done pushing the material out of it. So you can actually find glass syringes really cheaply on Amazon or other, lab supplier websites. And they're not too expensive. And what's nice is that, you can reuse them over and over and over again. I think VII makes the best ones. I like those.
So if you want to hear all this again, you can listen to once Luke's made it into a video or MP4. Remember, we're also doing the remix on Sunday, noonish Pacific time for the European audience. So if you want to hear it again or ask any new questions at the end, you're certainly free to join us for that.
Yep. And for these microemulsion systems, since they are, new, if you have questions, feel free to email me with them. And if I can answer, I will, or I can find someone who can. So if you're interested in working with these systems and maybe you're having a little trouble with them, feel free to reach out. And I think with that, maybe we'll wrap it up. So thank you everybody for coming. It was really nice to see everyone. It's been a while. So I hope you all stay safe. Thanks for staying awake and staying attentive for our new MCP version 11.
And
it was a great session. Very informative and engaging.
We haven't heard from Tierna tonight, but she's out there somewhere, and her birthday's tomorrow. So happy birthday!
Happy birthday, Tierna!
Happy birthday!
Oh, thanks for remembering, Chris. That's sweet.
All right, everyone. Thank you.
Bye, all.
Have a good night.